All right, for tonight's homework, we're going to do something a little different than the traditional, which is we're going to perform this lecture in a flipped classroom approach where I'm going to give you a short lecture based on some information that you know from before, as well as introduce what the actual trig functions and their graphs are going to look like. And then we will be using these graphs in class next time to answer some questions. So the first thing that we're going to do in this set of notes, which you have been given a copy of in class, what you're going to need to do, if you have not done that at this point, is we need to recall the terminal points of the special angles on the unit circle. Our special angles, if you'll remind yourself, are going to be the quadrantal family members, 0, 90, 180, and 270. And we also like to include our 360. We are also going to think of these in radian measurement and actually prefer the radian measurement. So you do want to go ahead and add your radian measurement, which matches all the way around. This is all just going to be kind of a practice activity. 3 pi over 2 and 2 pi. Now, for each family, I'm not going to fill in all the family members, but you do know your special families. Your 30, also known as pi over 6. Your 45, also known as pi over 4, and your 60-degree family, also known as pi over 3. So what I would like you to do is I would like you to take your family members, fill them in all the way around, just practice getting them, use your reference angle theta, pi minus theta, pi plus theta, and 2 pi minus theta way of finding the angles in the other quadrants for the family members. And then what I want you to do is I want you to take the terminal points, like for example, I'll do the quadrantal family, and write those right next to the location of the terminal point. So we would have here 1, 0, up here at the top, we would have our 0, 1. Over here, we would have our -1, 0, and down here we would have our 0, -1. And I do want you to fill those in for all the family members going across. So for example, if we're looking at pi over 6, our terminal point on the unit circle is going to be square root of 3 over 2, 1/2, and then you'll use the symmetry to get the special terminal points for the other family members that you have named. So what I'd like you to do right at this moment is go ahead and pause your video and take a minute or two, fill in your unit circle, and then hit play, and then check your answers with what I have on my key. So I'm going to go ahead, I'll hit pause, and then give you some time to come back and work. So I'm going to say go ahead and start filling out, and I'm just going to wait. And if you haven't hit pause before you keep going, because the answers are going to come up in about 2 seconds. So hit pause. Okay, go ahead and check your values against mine. Make sure that all of your points that, of course, that are in the first quadrant are both positive. That's the plus quadrant. If you're over here in quadrant 2, make sure that all of your points are of the minus plus variety. If you're in quadrant 3, all of your points should be the minus minus. And then over here in quadrant 4, you should have the plus minus. Now, the reason that we have laid these out is that what we want to do is we want to specifically start looking at patterns that we see on the unit circle to help us get some behavior of the actual trig functions in their graphs. Now, what we're going to be doing here is we're going to be thinking about this. Instead of having your input is going to be the cosine function and your output is your sine function, which is what you have right here. Your x is the cosine and your sine, or your y, is the sine function. What we want to do is we want to kind of think of this as, we like to call this the unwrapping function. So what we're going to be doing is we're going to input our x, is we're going to input the angle. And yes, typically when we do work with this, we are going to be dealing with radian measurement. We pretty much prefer radian measurement for these because it's a connection to the length. And then in a lot of applications, we can kind of get into the input will be time or distance or things of that sort, which are going to allow us to do some applications. Now your output, what we're going to do for our first one is going to be, we're going to do the cosine ratio, I believe, first. I'll see when I flip to the next page. But the output, you have to remember, is going to be your ratio. And it's going to be whichever one that you are looking at. And there are, of course, 6 of them, so we're going to have 6 functions that we're going to graph. Now, before we get into the graph, let's just remind ourselves a couple of things. Periodic functions are functions that have a repeating pattern, that their y values, after a certain amount of time has passed, a certain angle has been gone through, have a repeating pattern. And we have talked about that before. So the definition that we had from earlier is we pretty much said that any function where we can find some value, okay, so where there is some value, and that value, because we're kind of talking about the distance you're going to travel around the circle before you have a repeating pattern starting, it's a distance, so it's some value that is going to be positive, because we are talking about a distance that you have traveled around the circle, such that when I plug that new function value in, I take the LDEX and add that C to it, I get exactly the same function value as if I would have plugged in the original. And since we're talking about angles, we have this idea, remember our coterminal angle identities, that trig functions are going to be periodic because, for example, we know that the sine of any angle t is going to be exactly the same as the sine of that angle plus any 2 pi k, any angle that's going to make it coterminal, that's always true. So we have this idea that we're going to have a periodic function here because coterminal angles, their trig functions are exactly the same. And then we come in and we start talking about the period of the function. Okay? And the period of the function, you can't just say that it's always going to be 2 pi. It is going to be the smallest value of C for which there is a repeat. Or a repeating pattern. And this is important because while we know that all of the trig functions are going to definitely repeat after you go a distance of 2 pi around the circle, some of them may repeat more often than that. They definitely repeat every 2 pi, but they might repeat every, say, pi. And so when we talk about the period of a function, we want to try to figure out what is the smallest value for which there is a repeating pattern. When do I start over again? Now, and then once we have the period of a function, okay, then usually we want to start talking about the frequency. And if you think about it, the period is the distance it takes you to get from the beginning to the end of one cycle. Okay, so you can kind of think of this as distance per cycle, and then the pattern repeats itself. The frequency is going to be the idea that it is the reciprocal. It is the number of cycles per a certain distance. How frequent is it? So, for example, in one trig function, suppose that there is, and I haven't talked about which one yet, but I just want to give you an example. Suppose we know that it does have a period of 2 pi radians. That is going to take you a distance of 2 pi radians around the circle, and then the pattern is going to repeat itself. So we say the period is 2 pi. So it is a distance, 2 pi radians per cycle. That's kind of the idea of what we're thinking about it. So then I want to talk about frequency. How frequent is it? Well, the frequency is nothing more than the reciprocal, which in this case would be 1 over 2 pi. And instead of, because this is the distance per cycle, radians per cycle, this would be cycles per radian. Now, it might be more helpful to think of another example that might be after we've done some applications in this. Suppose I know that the period of a trig graph is 2 seconds. We're going to actually do an application here. So if it takes 2 seconds before the graph or the pattern starts to repeat itself, how frequent is it? Well, if the period is 2 seconds, the frequency is going to be 1 over 2. Now remember, this was 2 seconds per cycle, so this is a half a cycle per second. So do you see kind of the idea that period says the distance or time to complete a cycle, whereas your frequency is how many cycles per unit of whatever it is you're doing for your time or distance or angles that we're looking at. So the general relationship is going to be that frequency is always equal to 1 over the period. They are going to be reciprocals of each other. And we'll see this coming up in multiple applications that we're going to be looking at. All right, the midline of a graph. The midline, you can kind of think of that as the average. That as these functions are following this repeating pattern, there's going to be kind of a middle of the graph. Because the pattern repeats, we're going to have this idea that we're going to have a high and a low, and then we're going to come up with this average line. So the average is going to be what we're going to be looking for the midline. And then our last terminology that we're going to look at, and a lot of this will be a little bit more clear when I get to the actual graphs, but the amplitude kind of sounds like your altitude, which was kind of like height in your triangles. You can think of amplitude the same way. This is basically the height of the function above your average, the height of the function above the midline. And we'll talk about that when we take a look at our trig graphs here on the next page. So let's go ahead and go to the next page. Let's actually get a graph in here and kind of see what's happening. Now I'm actually going to kind of toggle between the unit circle on the previous page and this little information that I have over here. Now what we're going to do, and the idea is what we're going to do with the unit circle, which I have over here on this page, is I want to think of this point right here on the circumference of the circle. I'm going to consider this to be kind of the 0 on the x-axis, kind of where the origin is going to be. Because in this direction, remember, we're going positive, and in this direction we're going negative. So the idea is think of this like I'm going to take a piece of string, and it's wrapped around here, and I'm going to take it apart and unwrap it, and this is going to be a number line, except the number line that I am going around the circle, that number line is going to have not 1, 2, 3, 4 on it. It's going to be a number line that has the angle measures marked on it going around. And I'm simply going to kind of cut the circle and straighten out this circumference until it becomes my x-axis. So you'll see over here that what I have, and I'm going to zoom in just a little bit for you here, which you can see it probably better on your own paper, is you can see that I have all of these angles kind of located right here. This actually was the unit circle arc going around. We actually like to call this, a lot of times you'll see books, they'll call this X, but a lot of times they'll come in and they'll call it T, because they like to use that variable to kind of represent that this is actually a distance and arc length on the unit circle, because that's basically where you're getting these measurements from. And so if I was kind of coming back in here and before I actually do the graph, from 0, which is right here, up to pi over 2, which is right here, what quadrant is that really referring to on the unit circle? That's quadrant 1. From pi over 2 up to pi, which is this next little section, that's going to be quadrant 2 from our unit circle. From pi to 3 pi over 2, that's going to be our quadrant 3. And from 3 pi over 2 to 2 pi is going to be our quadrant 4. So the idea is we've unwrapped it, and this is the angles that went in the positive direction, because we started at that positive x-axis in that unit circle, and we went counterclockwise around, and that gave us our quadrants going in this order, and they followed these angles going around. Now, coming back here, let's talk about that. Now remember, when we went in the negative direction, you're going clockwise or you're going backwards through your quadrants. So if I'm looking at this from negative pi over 2 to 0, that actually is quadrant 4, because remember, you're working backwards. And then you end up in quadrant 3, and then you end up in quadrant 2, and then we end up back here in quadrant 1, and then it starts over. Okay, so that's kind of the idea. And when you're looking at this, clearly you can also see that they're going to be periodic functions, because you can see that the start, you're going to run through all the sine function values for quadrants 1 through 4, and then what are you going to do? You're going to start over again. And then after I get to here, I'm going to start over again. So really what I have shown here in this graph, this is going to be a graph where you're going to show 2 periods of the graph, because for the sine function, it's going to repeat every 2 pi, and that will be the smallest value. We'll kind of prove that here in a second, that the period is going to be 2 pi for this graph. Now, what I want to do, now let's go back to the unit circle and let's think about it. First thing is where was sine positive? Remember, all students take calculus, so all students take calculus, or our nice other version, which was all-star trig class. What quadrants, and there should be 2 of them, where is sine positive? In quadrants 1 and quadrants 2. And remember, when I say where sine is positive, I'm talking about the ratio is going to be positive. And remember, what we're doing here is we're inputting this angle, or arc length, however we want to refer to that. Our output, our y in this problem, is going to be the ratio. So I can kind of come down here, and this is all just pre-work for it. I know that sine is positive in quadrants 1 and 2, and negative in 3 and 4. So negative in 3 and 4, positive in quadrants 1 and 2. So if we're thinking about the y being positive, remember that this is going to mean above the x-axis, and then if the y value is negative, it's going to be below the x-axis. So that's going to kind of start to see a little bit of the pattern that's there. If I were to ask you for what values, which quadrantal angles, coming back over here, where is the sine ratio going to be 0 for which angles? We know the sine is the y coordinate on the unit circle, so it's going to be 0 here at an angle of 0 or 2 pi. It's going to be 0 here for an angle of pi or 180. So when I'm thinking about the fact now, when does that occur? It occurs here at 0, so I have a 0. Here at pi over 2, nope. Over here at pi, that would be a 0. Over here at 2 pi, that would be a 0. When your y value is 0, what do we have on the graph? You have basically an x-intercept, because the x-intercept is where your y value is 0. These are all the inputs for which your y value, your sine ratio, is going to be 0. So we have x-intercepts in all of these locations. Now let's come back to our unit circle again. And let's look at our values that we have. Now we do have this idea of what range of values we're going to be getting for our sine function. Because remember, your sine of theta, if you went back to the triangle world when we were doing this, is going to be your opposite over hypotenuse. And that was when we were in triangle world. And then we went into our terminal point world, where it's going to be the y coordinate over the hypotenuse, which is the radius of the circle. Now, if I'm looking at every point, every terminal point going around this unit circle, or actually any circle in general, if we're thinking of this as our trig ratio for sine, which again is the y coordinate going around, what do we definitely know about the relationship of the hypotenuse to the opposite side, if I was in the triangle, or the radius to the magnitude of y? And hopefully you'll say, well, of course, the radius, which is the hypotenuse, has to always be the longest section. So this y over r is always a fraction. It is always going to be something. Now, we strictly can go, it definitely has to be less than or equal to 1. What's the only case where you'd be 1? Oh, that's over here at pi over 2. But the only choice is for this to be a fraction. Now, of course, you have to take into account that y could be positive or negative. And so I have fractions. I'm 0 here. Okay. I'm up to 0.5. this is about, I think, 0.7-ish. Okay, you can test it in your calculator. This is 0.8-ish, somewhere around there. And then I get up here to 1. Then I come over here on this side, and now I'm going back down. So there's this idea that as I'm coming through this quadrant, each of these values are increasing up until I get to 1. And then I move into this quadrant, and they are now decreasing. So I have increasing, decreasing. What must this value be? If you think about a graph where you have switched from increasing to decreasing, that must be an extrema, a maximum value on the graph. So we know that the 1 is going to be a max. Okay, so 1 is going to be our max. I come around, I've decreased to 0. What happens when I hit here? Oh, I have negative numbers. When I'm coming around for the negative numbers, these are becoming more and more negative. So I'm still decreasing, and I'm decreasing down until I get to this -1. And then I flip into this quadrant, and now I become less negative as I head back to 0, and so now I'm increasing again. So at -1, that ratio is going to be our min. But the sine ratio is kind of captured in between that max and that min. So now let's come over here and put that information on our graph. We know that at pi over 2, which is where you had the value of 1, that was going to be my max. And then over here at 3 pi over 2, that's the location of where that min value was. And then I'm going to remind myself that in quadrant 1, I was increasing up to that max. Then I was still positive, but decreasing back to 0. And then I decreased a little bit more, became more negative down to the min. And then I started increasing again, coming across. Now we could fill this in over here as well, but it's going to be a repeating pattern. So let's think about what we have here. I'm going to put some key points in. I know that at an angle of 0, the sine ratio is 0. I'm going to add down here anchor points. 0, 0 is going to be one of them. All right, the next point that was important, we're going to be increasing here throughout quadrant 1. We'll put some points in a second, but then I hit this max point at pi over 2. So pi over 2 had a ratio of 1. So this point is going to be pi over 2 is your input, and your output is your ratio. Input angle, output sine ratio. And so pi over 2, 1, let's add that to our list. Okay, and kind of writing down kind of important reasons why I'm picking these anchor points. That one's an x-intercept. This one is going to be a max. All right, so then the next thing I'm going to get is there's my x-intercept. This 0 right here. So what are the coordinates of this point? This point is going to have a coordinate of pi 0. So we come down here to the bottom. Let's add my pi 0 into my list. Another x-intercept. All right, and then we're going to keep going. We're going to decrease through this quadrant, and then I get to that min value, and I'm going to consider that to be a special point. So I'm going to plot that. Its coordinates, 3 pi over 2, -1. So let's add 3 pi over 2, -1 to my list. And then I'm going to increase back through this quadrant until I get to my x-intercept at 2 pi 0. So we'll label that, and 2 pi 0. And that pretty much is going to be our key points that we're going to have. This was a min, back to an x-intercept, because what happens after that? The pattern starts to repeat. Now, of course, I could get a few more points in here. Like, do I want to just make this like a little sawtooth jagged edge? No. If you think about pi over 6, what was the sine of pi over 6? The sine of pi over 6 is 1/2. So that point would be about there. I'm not going to label it. I'm just going to put it in. All right, the sine of pi over 4, that 1 over root 2, is 0.7-ish. So a little bit higher, but not quite halfway in between. And then my pi over 3, my sine of pi over 3 is 0.8-ish. So it comes up. So instead of this being pointy, do you see how I'm getting a nice curve coming in here? And then I get onto this side. Remember, if you're in the same family, The sign is the same in quadrant 2 because it's positive. And notice that here's pi over 3, here's 2 pi over 3. Oh, look, those would have the same ratio. They would have the same height. And then my 3 pi over 4 would be the same height as pi over 4. My 5 pi over 6 would have the same height as my pi over 6. Because the trig functions in quadrant 1 and quadrant 2 were the same, but remember, because we unwrapped it, that this is the pi over 3 family here and here, and then it's the pi over 4 family, and then the outside is the pi over 6 family, because if you look back, just want to get those points off so we don't think they're points. If you look back on the unit circle, you can see kind of the order that you're traveling through the points. You know, you hit pi over 6 first, because that's the smallest measurement, and then you hit pi over 3 next. Over here, then you hit your 2 pi over 3, and then your 5 pi over 6 and your pi. So there is an order to the angles as we move them around the circle as they are in order coming in here. And then the only difference is when you get over here into your quadrants 3 and 4, the trig ratios are the same except they're now negative because you're in quadrant 3 and 4. So your 7 pi over 6 is going to be negative 1/2. So that's going to come down here. And your 11 pi over 6 is going to be negative 1/2. Same height. Your 5 pi over 4 is going to be your 0.7-ish. And then your 7 pi over 4, 0.7-ish. And then your pi over 3 family members are about 0.8. And now we don't always plot those points because once you get the idea that it's going to be curvy and not pointy, that you know that you can basically just have this point, this point, this one, and this one, and that's enough to see the pattern, and you'll know that you're just going to fill in the curve and making it nice and smooth and curvy, and you create what is essentially a wave. Now, and then the nice thing is when you come back into this quadrant, I'm just going to go, I like to go, this is the beginning of the period, this is the end of the period. So I like to back myself up to the beginning again. So over here is going to be the beginning, and notice I'm going to go intercept. I'm going to move over a quadrant and then do max. Then I'm going to move over a quadrant to the next quadrantal, and I'm going to go intercept. Move to the next quadrantal, do min, and then you would be back to your repeat. And then you can fill in the nice curve. You don't have to plot the points. Just fill in the nice curve. And we can fix it if we get a little bit off. Let's connect here. That's what we have erasers for and why we're doing this in. Well, you're in pencil, but I'm in the magic pencil, so I can erase. And then basically the idea is you can think of this one little thing as a rubber stamp that I pick up, and then I'm going to stamp over here, and then I'm going to pick up, and I'm going to stamp over here again, so I can kind of have this idea that I can say that it continues, but I know it doesn't continue up. It's going to continue going up and then back down and then up and then back down. And that is going to be the picture. This is our picture of the sine of x. Now let's talk about going back to some algebra topics that we had. The domain of a function. What are the types of things that we can input into the function and get a defined value back? Well, every angle has a sine ratio because every angle has a y-coordinate going around the unit circle. So the domain is really going to be negative infinity to infinity. Every angle has a sine ratio. Done. But now our range, what were our ratios? Our min was -1. Our max is going to be 1. So our range, kind of fit it in right here, is going to be -1 to 1. And then can you see here, like this is what we call, this piece right over here, is what I'm going to be calling the fundamental period. And that fundamental period, because that's kind of where the big repeat is coming from, that first time that I have it, that fundamental period, what is the distance from the beginning to the end? The distance is 2 pi, and then I started to repeat the pattern over again. So that's what, again, you can see why I chose the period to be 2 pi for this function, which means its frequency, which you will recall is 1 over the period, if you need to remind yourself of that. your frequency is going to be 1 over 2 pi. Now, I like to add in kind of an idea of units. This is going to be, because I'm thinking of this as arc length or angle, this is going to be, in our angles are in radians. I can think of this as how many radians per cycle. So you can see why I'm calling this a cycle. That's going to get repeated. And then over here, this is going to be cycles per radian. Okay. Now for this graph, what I would like to do is take a look at the amplitude. Now remember I said the amplitude was the distance above, how far above the function went above its midline. Well, the midline was the average. And if I'm thinking about this set of points here, can you see that it's exactly half of the points are above from quadrants 1 and 2, and exactly half of the points are below? It exhibits some really nice symmetry that if I were to slide this over, they would be mirror images of each other. So would everybody agree that the midline really here has to be the x-axis? So for the parent graph, without any transformations, which we'll talk about shortly, the x-axis is going to be your midline. Usually, though, we don't like to write it as x-axis. We like to write the equation of the x-axis, which is a horizontal line. And the equation of a horizontal line, if you'll recall, is y equal to 0. So this is usually what we're going to be putting down for our parent graph. This is before we do any transformations of it. The sine parent graph is going to have a midline of y equal to 0. Okay, so essentially, I'll put this in a nice, I'll put a little yellow going across here, that this is the average of all the points, that this is going to be the middle of the graph that we're looking at. So that's my midline. Now I want to look for this idea of an amplitude. Now the amplitude is how far the function goes above the midline. Well, here's the midline, and I want to know this distance right here is going to be my amplitude A. And how far do you go? How far was it from the middle, 0, up to the max, 1, a distance of 1. So the amplitude is going to be 1. And in terms of notation for these things, we do call amplitude A. Midline we just write out. Frequency, I usually use lowercase f to refer to that. If I'm talking about period, I just use capital P to talk about period. I do think some textbooks will use T, capital T, for some reason, but I'm not really, and I can't remember exactly what your textbook does. But you'll see kind of in the formulas for the textbook what they're using. I'm going to use capital P when I'm talking about it. And then the other thing that I like to add here is the fact that the pattern that I have going here, I like to think of this because when we start working with these functions, this is going to be the pattern that is followed for pretty much every sine graph that we look at, which is going to be, I'm going to do I for intercept, capital M for max, I for intercept, lowercase m for min, and capital I for intercept. And even when we start moving this graph around, we're going to be transforming this graph. Basically, if you want to think of it as like moving it up and down, shifting it left and right, and moving it around, the idea is we're going to be looking for this pattern. And this wave pattern of intercepting with the midline, max, intercept, min, intercept. And I'm going to use that kind of as a way to figure out the pattern that's going on when we start doing our transformation. All right, so let's take a pause there. And what I'd like you to do over on the next page is the cosine graph. So I want you to kind of repeat the process of what I did for sine for cosine. And I want you to bring this with you to class next time. And then we'll pick up from that, but this will be kind of your introduction. We'll get the sine and the cosine done based on this. Okay? And when you get kind of to the end of this part of the activity, and you should have everything that I have over here on the sine graph, even these little pieces of information, labeling the quadrants, putting what's positive and negative, putting your intercepts, and putting in your increasing and decreasing. I want to see that for the fundamental period, which is going to be this 0 to 2 pi. You need to label your x and your y-axis just like you did here. And I want you to label the key points that are on the fundamental period. And just to be thorough here, I'm going to go ahead and label 0, 0. So I have all 5 anchor points, the ones that I'm going to use in transformations, labeled on my graph. Even though you're not labeling these points, I want to see you plot the points for the family members to help you when you sketch this fundamental period. And then you'll use the pattern in order to graph the function. So you should have this completely done for the cosine when you come to class next time. When you come to class, we will then discuss the other 4 trig functions kind of together in class.